Hello and welcome to another video for Reigate Maths based on the working through examples for the Edexcel Decision Maths unit for the further maths specification. Today we're going to be looking at the Big M method for solving a simplex linear programming problem. So this is the problem we're going to be looking at today. So we're going to be maximizing p equals 3x plus 2y, subject to the constraints there. Now the setup to the Big M method is very similar to that for the two-stage simplex method. We're still going to introduce artificial variables, surplus variables and slack variables like we did before. So let's start by doing that. Okay, so with our two inequalities, we've got 2x plus y plus s1 equals 6 for this one here, and then 3x minus 2y minus s2 plus a equals 4. So pretty much the same as with the two-stage method. Now this is where things get a little different. So with the two-step method, or two-stage method, sorry, we introduced a new objective function made up of the sum, or the minus sum, of all of the artificial variables. We then made that equal to 0, and if we can, then we found a basic feasible solution. With the Big M method, we introduce a arbitrarily large variable, and we include that in our original objective function. So thereby starting at the origin, so remember x and y have to be the origin. Okay. X and y start at the origin, and so what we're going to do is we're going to take away an arbitrarily large value times by a, thereby ensuring that when we reduce a to 0, we're going to hit the feasible region, ideally. Now if we can't do that, so we'll see, I'll talk about a little bit later about when that doesn't work, but there are sort of pros and cons of both Big M and two-stage. So two-stage is useful because it finds whether there is a basic feasible solution straight away. That's kind of what it does well. Big M tends to do the whole simplex a little quicker, I find, but you don't know if the solution you find is feasible until right at the end. So it's a toss-up between the two. Now the reason we introduced the variable m to be arbitrarily large is so that numbers like 6 minus a half m, for instance, we're ensuring that that is negative, or less than or equal to 0, and that numbers like 3 plus 3m, which we're going to see later, are definitely positive, because that's what we need to be looking for simplex. So what we do is we say, okay, we've got our maximize function here. This is very important. If the problem is minimized, you need to change it to maximize first. And we're going to say p is equal to 3x plus 2y minus some massive number times a. We don't know what the massive number is, we just know it's big. We then approach eliminating a from our objective function in the same way that we do for the two-stage method. So we rearrange the equation that has a in it and then get rid of it here. So p is going to be equal to 3x plus 2y minus m lots of 4 minus 3x plus 2y plus s2. we now need to expand it and collect the like terms. Remember, m is a number. All of the variables are my lowercase letters, apart from p. So, if we expand and simplify, we're going to get 3 plus 3m times x minus plus 2 minus 2m y minus m s2 minus 4m. Then, like before, we need to get all our variable terms over to one side and numbers on the right. So we're going to end up with p minus 3 plus 3m x minus 2 minus 2m y plus m s2 equals minus 4m. Now, very important to note and pay attention to where the positive and negative numbers are. This bracket is positive, so this is a minus number. This bracket is negative, so this is a negative number. We're now ready to start our simplex. So, we start our initial Tableau with our basic variable column. Now we can see our basic variable here is S1, here is A, and in our objective, as usual, it's P. We've got a lot of variables, and notice how these are brackets, so make sure you space out and you lay out your working appropriately, just so you've got some space. So X. So I'm going to do the objective row first, just so I can make sure I've got my spacing right. So we've got minus 3 plus 3m, y minus 2 minus 2m. Now, obviously you could write that as 2m minus 2. I don't know why, just don't. Okay. S1, we don't have any. S2, we've got m. A, we don't have any. And then value, we've got minus 4m here. And don't forget, normally, in the normal simplex ones, where we have only less than or equal to's, our starting value for p is 0. But our starting point is not in the feasible region. Okay? Because we've got a here, this answer, or this initial solution, is not feasible. So it's okay for p to be minus. Because what we're going to do is we're going to take p as a massive minus number and increase it so that it first hits the feasible region, ideally, and then moves around inside it. So we now fill in the rest of it. So our first row here, we've got 2x, 1y, 1s1, none of those, and value is 6. 3x minus 2y, no s1s, minus 2s2, 1a, oops, minus 1s2, and then 4 here, and we're ready to go. So, calculating our pivot, as normal, we can see here, this is a big minus number, this is actually a positive number. So the only option for our pivot column is x. So we work out our theta values. Well, that's 1.3. And we find that our pivot is in row 2. Which is handy, because we can see we're going to eliminate A. We're going to make A non-basic, which means chances are, unless something disastrous happens, our final solution is going to be feasible. So we do our first iteration. Okay, with our objective rows. So we've got our basic variable, x, y, s1, s2, a value and row operation. Now, with the graphics calculators, obviously there's a problem with putting in M. We can't do it. So, what I tend to do instead is I just put in some big number instead of M. The reason being, it helps us really spot our calculations. It's not the end of the world if you don't, and you can just use your graphics calculator to do the first 2 rows, but I like having all 3 rows there, and it helps me see what's going on, personally, so that's up to you. So, as normal, matrix, we have a 3 row, 3, 4, 5, 6 column, so we've got a 3 by 6. So we've got 2, 1, 1, 0, 0, 6, 3, minus 2, 0, minus 1, done that again, 1, 4. Now, I tend to choose a number that's big compared with these. Not too big so that it just messes up the layout, but big enough so that it's very different. I'm going to use 1,000. Okay. Now, if you can't do the arithmetic in your head, that's fine. You can just type in the calculation in there, and it does it for you. Now, make sure you are using the same value of M for everyone, otherwise it's going to go wrong. And we're ready to go. So, row operations. So, we need to make our pivot row, row 2, 1, so we're going to do, third R2. So, just as a reminder, you go to the times row, we've got a third times row 2, and we can see that's become a 1, and we just copy it down. So we've got 1, minus 2/3, 0, minus a third, and then 4/3. The basic variable swaps from A to X. We've now got to do our top row. So we've got minus 2, lots of R2 plus R1. That's going to stay as S1, that's going to stay as B. Okay, so times row plus F3, minus 2, row 2, row 1. Okay, and then we write it down again. 7/3, 1, 2/3, minus 2/3, and then 10/3. Now this is where things get potentially a little tricky. We need to do 3 plus 3m, lots of R2 plus R3. And this is where the graphics calculators I find are very, very useful. So we're going to do 3 plus 3 times 1,000, lots of R2 to R3. And you can see, without doing any algebra, we've already got rid of some m's. So we've got 0, minus 4, 0, minus 1. If we scroll along though, we can see, oh look, we've got 1,001. That's a big number, but we know m is 1,000. So without doing any algebra again, this is m plus 1. And if you look and see, we've actually eliminated most of the m's from the bottom row, which is good. This is a massive positive number, which is great. These are negatives, so we're going to be choosing this one as our pivot row column next. And we don't really have to worry about m's anymore. So, this is not optimal, so we need to write that down. Since there are negatives in objective row, so we need to go again. We can see that the pivot's going to be in the y column, because we've got minus 4 here and minus 1, and we want the most negative number. We can see as well that the theta values, we're only going to get one of them, because if we do 4/3 divided by minus 2/3, we get a negative number, which we don't want. And this is where the graphics calculator again becomes very, very useful. Because you can see we get 10 over 7. Which means we're going to get a lot of stuff in our table, our Tableau, over 7. Which is annoying, but oh well. So pivots here. So we go again. So we've got basic variable x, y, s1, s2, a, value, row operation. So we can see here that our basic variable s1 is going to change to y, then x and p are going to stay the same. Now our row operation we need to make this a 1, so we're going to do 3 over 7 lots of r1 times by row, 3 over 7 lots of row 1. So it changes it to a decimal, but oh well. We can see when we highlight things, it still says 3 over 7. So we've got 0, 1, 3 over 7, 2 over 7, minus 2 over 7, and 10 over 7. As we'd expect, remember the value will end up being the same as the theta value in the objective row. Okay, we now need to get rid of this one, make this a 0, so we're going to do 2/3 r1 plus r2. So 2/3 r1 plus row 2. And there we go. So 1, 0, 2 over 7, minus 1 over 7, 1 over 7, and 16 over 7. We need to do 4 lots of row 1 to get rid of the 4. So 4 r1 plus r3. Right, so 0, 0. Now we get some annoying numbers. 12 over 7. Ooh, that's positive, that's useful. 1 over 7, still positive, still useful. This is where things get a little pickly, but just pay attention to what we've got. Remember, m is 1,000, or we're saying m is 1,000 for our graphics calculator. So we need to think, okay, this is nearly 7,000. So this is nearly 7m. This is 7m minus 1. So this is 7m minus 1 all over 7. So you can write it as m minus a seventh if you prefer. I'm not fussed. Okay, and then we get 68 over 7. The important thing is 7m is big. So 7m minus 1 is still positive, and we can see that this is a positive number. We chose 1,000, which is a nice big number. So, this is optimal. We can also see that A is not one of our basic variables, which means this is a feasible solution. The solution actually works. If we were left with A here, then although we have an optimal Tableau, the solution itself is not feasible. So that's the downside of big M, is that you don't know if it's feasible, most likely, until right at the end. But this one is optimal. So we need to write that down. So optimal, because there are no negatives in the objective row. So therefore, the maximum value of P is 68 over 7. Where x equals 16 over 7, y equals 10 over 7, and then s1 equals s2 equals a, which is 0. And we're done. I prefer big M to two-stage simplex method because it tends to be shorter and I don't mind algebra. The reality in the exam, though, is you'll be told which one to use. But if you're told to use big M, then you can count yourself lucky, because it's a little bit nicer. Again, if you have any particular topics from any of the Maths A-Level or further Maths A-Level that you'd like me to do a video on, please do let me know. Otherwise, thank you very much for watching.